Hi guys, this is Dr. G here, and in this video we will talk about cis-trans isomerism in cycloalkanes. So when it comes to cis-trans isomerism, it is a primary group of isomers that falls under stereoisomers. So stereoisomers are basically isomers where you have the same chemical formula but atoms are oriented differently in 3D space. So you have the same chemical formula and structures are very similar, but the only difference is that the atoms could be arranged differently in 3D space. So as compared to constitutional isomers where you have different obviously different chemical structures, stereoisomers could be a little bit tricky. Okay, why? Because you might have to worry about how atoms are arranged in 3D space in order to understand stereoisomers. And these cis-trans isomers specifically, they fall under geometric isomers, and usually this cis-trans isomerism is present in cyclic compounds like cycloalkanes and also in alkenes. So alkenes and cycloalkanes are the prime targets for cis-trans isomerism. So let's talk about why this cis-trans isomerism is possible for cycloalkanes. I mean, we don't see cis-trans isomerism for alkanes, mainly because alkanes only have single bonds, and then around single bonds you can easily free rotate the molecule, right? So around a single bond you can easily free rotate a molecule to obtain different conformations. We learned that in conformations lesson. But when you have a cyclic compound or a cyclic alkane in this case, okay, so even though you have carbon-carbon single bonds, the rotation around these carbon-carbon single bonds, the rotation around these carbon-carbon single bonds are restricted. Why? Because you have a ring. So you have a defined structure for a ring. So therefore you can't free rotate these carbon-carbon bonds. Because of this hindered free rotation around the carbon-carbon single bonds in cycloalkanes, you usually see cis-trans isomerism. So because of this restricted motion around carbon-carbon bonds that are involved in cycloalkanes, you actually have two different phases for cycloalkanes. You actually have two different phases for cycloalkanes. You have a top phase and you have a bottom phase. Okay, so in this example, we can say this side right here is your top phase, and then this is your bottom phase. Okay, so when you have two different phases for a cycloalkane, if you have substitutions on these cycloalkanes, these substitutions could be present in the same phase. In this case, both CH3 groups are on the top phase, or sometimes these substitutions could be on opposite phases. Okay, the difference between having the substitutions on the same phase or opposite phases is that since you can't rotate around these carbon-carbon single bonds, the bottom phase will never see the top phase and top phase substituents will never see the bottom phase. So therefore, they are completely different. When you consider the three-dimensional aspects, when you have two substituents on the top phase is completely different from having two substituents on opposite phases. So therefore, we have to consider them as isomers, and that is exactly what we do here. Even though this 1,2-di methyl cyclopropanes have the same chemical structure, the arrangement of the two substituents, the two methyl groups, is different based on the location of the CH3 groups. So therefore, they fall under cis-trans isomerism. So if the two substituents are on the same phase, it could be top phase or bottom phase. Okay, if the two substituents are on the same phase, then we call it cis. Okay, and if the two substituents are on opposite phases, like in here, bromine is on the top phase and the ethyl group is on the bottom phase. So if the two substituents are on the opposite phases, we call it trans. So that is how you identify the cis isomer and the trans isomer. In the cis isomer, you have the two isomers on the same phase, and in the trans isomer, you have both isomers on. You have the two substituents on the opposite phases. Okay, so now we are going to learn how to draw trans isomers. So as an example, I'm going to use a cyclohexane in this example. Why is this cyclohexane? Because you have 6 carbons in this ring, right? So if you have 6 carbons, it is a cyclohexane, right? So if you want to draw a trans compound or a trans isomer, for a cyclohexane, you have to have two substituents. That is the first requirement. You have to have two substituents. So in here, let's take two methyl substituents. Let's take two methyl substituents, and of course you should have one methyl substituent on one plane and the other methyl substituent should be on the opposite plane. Okay, so usually in here this wedge wedge identifies one methyl. You can write CH3, but it doesn't really matter. Okay, if you are using skeletal formulas, you don't have to write a CH3. Okay, every end and a bend is a carbon, right? So you don't have to show them. But the most important thing that you have to remember is that one substituent should be on the opposite plane as compared to the other. So if you are using a wedge to draw one CH3 group, you should use a dash to identify the other substituent. Okay, other substituent. So the location of the two substituents, the carbon that contains the substituent doesn't really matter. Okay, so let's draw another one. Okay, here one methyl group is on a dash line. That means it is going into the plane. Okay, and then let's draw the wedge on this carbon. Okay, so this is coming out. Once again, only thing that matters is that the two substituents are in opposite planes. Okay, so this could be chlorine. Okay, let's see, this is chlorine, Cl and Cl. Okay, and then let's draw another isomer, trans isomer. So this time let's use a bromine. Okay, let's use a bromine. Okay, and then the other should be on the opposite plane. So if you use a wedge, the next one should be a dash. Okay, so here is the other bromine. Okay, you can also use chair conformations. Okay, if you don't understand chair conformations, we will talk about chair conformations in a different video. So for now you can move forward. Okay, you can move forward if you don't understand what is a chair conformation. Okay, so for cyclohexanes you can have a chair conformation. Here's the chair conformation, and then of course since this is trans, one substituent should be on axial. One substituent should be on the top plane and then the other substituent should be on the bottom plane. Okay, so let's say this is X and Y substituents, so these will be trans. Why? Because X is on the top plane, Y is at the bottom plane. Let's take the axial position. Okay, let's take the axial position. So let's say one substituent here and the other substituent is right here. Okay, so this will also be trans. If you want to take a different carbon, okay, let's take this carbon right here. Okay, so in here the X group is going down, right? So the other group should be coming up. Okay, so this is trans. Why? Because X is going down, or it's on the bottom plane. Okay, it's on the bottom plane, and Y is on the top plane, or it's coming up, right? So all you need to do when you are drawing trans isomers, all you need to do is make sure to put the two substituents on opposite plane. Please put the two substituents on the opposite plane. All right, let's learn how to draw cis isomers. Okay, let's try to draw cis isomers. Okay, so the difference between cis and trans is that in cis isomers you have both substituents on the same plane. Okay, so let's take the same cyclohexane ring. Okay, here is our cyclohexane ring. Okay, so if you put one substituent on the top plane, okay, if you put one substituent on the top plane, other substituent must also be on the top plane. So when you are, how do you show the top plane? You use a wedge, right? So put both substituents on a wedge. Okay, I hope this is clear. All right, so if you're using a dash, then both substituents should be on a dash. Okay. All right, so both these isomers will be cis. Why? Because both substituents are on the same plane. All right. Now we are going into a sample problem. So I actually want you to pause the video and see if you could read and understand this question. That is the first thing. And then see if you could come up with an answer by yourself. Okay, so I want you to try this sample example. Okay, so in here, I want you to draw the structures of the following molecules. Okay, so I want you to draw a trans isomer for 1-bromo, 3-methyl cyclohexane. Okay, so that is the first question that I want you to do. I want you to draw a 1-bromo, 3-methyl cyclohexane. So if you take A, what are the two substituents you have? You have a bromine and you also have a methyl group. So these are the two substituents. You have a bromine and a methyl group. And then here the cycloalkane is a cyclohexane. So draw a cyclohexane. Here is my cyclohexane, and then the two substituents are on number 1 and number 3, right? So bromine is on number 1 carbon, CH3 is on number 3 carbon. Okay, so that is noted. And then let's identify the number 1 and number 3 carbon. So let's say this is number 1 carbon, then this is 2, this is 3. Okay, so these are the two carbons of interest, 1 and 3. Okay, so let's put bromine on number 1 carbon. I'm going to use a wedge. You can use a dash, it is up to you. Okay, so I'm going to use a wedge to draw bromine. You can randomly select a wedge or a dash for bromine. But now we know that this is a trans compound. So the other substituent should be opposite to bromine, right? So if bromine is on a wedge, the other substituent should be on a what? It should be on a dash. So the methyl group should be on a dash. So this is your answer. This is your answer. Okay, let's try B. So in here, I want you to draw a cyclobutane, and the two substituents are going to be methyls. Okay, so it's a dimethyl, so both substituents are methyls, and then it is a cis compound. Okay, so let's have a cyclobutane. Here is a cyclobutane, and then the two substituents are on 1 and 2, and it is a cis, so both substituents should be on the same side, right? So you can draw two wedges or two dashes, it doesn't really matter. Okay, so I'm going to use two wedges. Okay, and then that will be your compound. That will be your compound. Okay, if you want, you can write CH3, but it is not really necessary because we are using skeletal structures, so you don't have to write the carbons and hydrogens. And also you can do hydrogens, like, you know, you can show the bottom plane and then you can say there are two hydrogens in there, but that is not really necessary. Okay, so as long as you draw a cyclobutane ring and then put the two methyl groups on the same side, you're fine. Okay, so both these are acceptable answers. Both these are acceptable answers. All right, so here is my official answer. But I mean, I hope that you understand it now. So with that, we are going to conclude this video. And if you have any questions, please feel free to contact me. Okay, you guys have a good one. Take care.